So let's take a look at quality of service. We mentioned before in the CCNA voice videos some of the advantages and disadvantages to a packet switch network. And we'll remember that some of those disadvantages were such things as no dedicated connection, as with circuit switch networks. There was no inherent guarantee that the packet will ever arrive, so this would be translated as packet loss. There's not always enough bandwidth available. However, it is much easier to add than just about anything else. Delay can often occur at various router hops along the way. This is known as end-to-end delay, or dealing with all of the various hops within the end-to-end overall picture. And that delay can and often does vary greatly from hop to hop. So the variance of the delay, not the delay itself, but how much it varies from one hop to hop, or from one hop to a different hop, is known as jitter. So some of the types of delay: we have delay caused by DSPs, delay caused by packetization and or processing, delay caused by queuing, delay caused by serialization, that is actually putting the bits onto the wire in the electrical form, propagation delay, so how long it takes a packet to get from one router to another, just based on the speed of the transmission over copper or the speed of light over fiber. And then there's also, at the final receiving side, the de-jitter buffer, and that produces delay as well. So ways to mitigate issues surrounding bandwidth, or lack of bandwidth, I should say, delay, and packet loss. So some of the ways to deal with bandwidth, delay, and packet loss, one that would deal with all three, are just to increase the bandwidth. As I mentioned, this is the easiest thing to do. This will actually help to mitigate all three of those. Ways to deal with just bandwidth and delay, but not necessarily packet loss: we can try to transmit the most important packets, our voice and sometimes video, first. Another way is that we can compress layer 2 payloads, so that is the layer 3 and everything inside the layer 3, and or we could optionally just compress the layer 3 and or layer 4 headers. So this is IP header compression, that would be layer 3, or TCP, or actually RTP header compression. Sorry, not TCP, but RTP. And then some ways just to deal with packet loss: we can guarantee adequate bandwidth to the packets that are requiring it, and we can also prevent congestion from occurring by dropping less important packets before it begins. Now that seems counterintuitive, but if we have, if we have congestion, if we have the point where our buffers are full, whether those are our ingress or our egress buffers, and we can't hold any more, that is, the router just doesn't have any more, or possibly the switch just doesn't have any more memory to hold those packets or those frames, well, then packets or frames are going to be dropped. Once there's no more memory to hold them, well, the tail end of that, it all just gets spilled off into the bit bucket. If they're going to be dropped, and we know that they're going to be dropped because we're possibly running at maximum utilization. Now, obviously, if we just increase bandwidth, that deals with that, but we're getting down to maybe we can't just increase bandwidth. So if they're going to be full and they're going to be dropped, then we can choose to selectively drop less important packets. It seems counterintuitive, but you'd be surprised how much it can improve voice and video performance. Now, it doesn't necessarily improve the rest of your applications, but this just depends on your overall throughput and really, the size of your routers and switches and infrastructure. So taking a look at what is really quality of service, let's just provide a definition. If we could just sum it up, we would do so by saying it's the ability for us to provide consistent, predictable performance based on the provisioning of the network LAN and WAN devices to provide special services to traffic that we deem important, or sometimes we call it interesting traffic. Now, there's some important steps for provisioning QoS. And we're going to take a look at these. First is to identify traffic and its requirements. So we want to identify all types of traffic on the network, or at least most, maybe not down to every single type, but if you can, it would certainly behoove you to do so. It would be very beneficial. Determine how important each type of traffic is or is not to the specific business. And so if you're working in-house, then this is to your business. If you're working as a contractor or a consultant, then this may change as you move from client to client. And then determine requirements for service levels and response times per the traffic type. And this may also have to be done in conjunction with the client to determine what are their service levels. Next is to divide the traffic up into various classes. So maybe we have a voice and video media class. This is the actual RTP, real-time protocol. This needs priority and low latency. Then we might have a class, and we will have a class, for at least voice and video signaling, all the voice over IP signaling, and possibly, if we're doing clustering over the WAN, the ICCS, the inter-cluster communication signaling. This needs at least guaranteed bandwidth. Not necessarily priority. We don't need to get it out the door first, but we need at least guaranteed bandwidth. And then possibly other important business applications to the company that you're working with. So maybe things like SAP or SQL database traffic, maybe e-commerce. These might be given guaranteed bandwidth. It just depends on the priorities of the business. And then everything else, whatever we don't deem as really that important, we're going to give best effort, which is effectively no guarantee at all. Then we need to define the policies for each traffic class. We need to define the minimum and possibly maximum, we'll take a look at that, bandwidth that we should guarantee to each class. We should assign priorities to the classes that require them. This is the voice and video media. And we should manage any potential congestion. So let's take a look at some of the characteristics of voice and video and data traffic. Voice traffic is typically smooth. That is, it's typically flowing at an even rate. It's not very bursty. It's benign. It's not greedy for a lot of bandwidth. In fact, it's typically per call fairly low in terms of bandwidth and overhead. It's very sensitive to drops, and it's very sensitive to delay. It's based on UDP, so there is no mechanism for retransmitting like there would be with a connection-oriented protocol like TCP. These are things you learned about in CCNA, route switch. Okay, why is that? Why is our voice UDP based? Okay, UDP is I kind of shout in an empty room and I hope that someone else is on the other side of that dark empty room and they hear me. But I have no way of seeing them or knowing them, and they're not going to respond to tell me that they heard that. Now they may say something back, but it's not going to be an acknowledgement that they heard what I said. It's just going to be something they want me to know. Okay, this is the two-way voice communication, but it's based on UDP, so I don't know that each and every packet arrived. Why is that important that we don't have it based on TCP? Well, first of all, TCP takes a little bit of time to set up. Of course, I have to send them my initial packet, and they have to send me back an acknowledgement, and then I have to acknowledge their acknowledgement, the three-way handshake, right? The SYN, SYN-ACK, and ACK. But after that, every packet has a sequence number, basically. And if I don't receive all the packets that I should, then I tell the other person, oh, you missed some, retransmit. Now, maybe the network dropped them or whatever. If I tell you to retransmit voice packets, and you have to, one, assemble them in the right order, and two, retransmit anything that is lost, by the time I've told you to retransmit, and by the time that you've retransmitted, and by the time I receive that retransmission, it doesn't make any logical sense to the hearer, to the person listening anymore, right? Because all of a sudden I'm receiving a small blip of a word, or maybe even a small part of a word that was said 3 words back, right? Or maybe even 2 words back. And it wouldn't make any sense to the hearer to hear that way, way, way out of sequence. So well, actually, that's a bad example. I was trying to give you a good example of what it might sound like, but that's more just drop packets in general. Okay, so it's important that we actually use a lower overhead layer 4 protocol such as UDP, and that if packets are dropped, they are. Now, that's why one of our requirements is that we have, for a voice network, we have packet loss that is less than or equal to, but really hopefully less than 1% of all packets are lost. Okay, so we can't have a high packet loss because it is UDP based. But it's also the fact that if we should drop packets, let them go. And yes, someone might miss a little bit of a word, but there's something called the human retransmission. And it's this. All of a sudden I hear, and then I didn't hear exactly what you said right in there, and it didn't make sense. It didn't flow. And so I say to the person on the other end, I'm sorry, could you repeat that? So there's the human retransmission that takes over for the lack of the network. But it's important to know and think about and realize that these are the reasons why quality of service is so crucial to voice and video communications, because we can't get voice or video frames out of order, and they really make too much sense unless we have massive receive buffers, and then it becomes a complete walkie-talkie communication, right? Hey, Joe, how are you doing? Fine, Mark. How are you? Oh, I'm good. I got your call the other day. Well, anyway, I won't keep going on, but it becomes this huge delay to buffer everything. You know, if we were using TCP, make sure that we assemble everything in the right order, or, submit retransmits if we lost things. And it doesn't make sense anymore to try to communicate. It just becomes completely psychologically frustrating. And of course, voice traffic needs priority to deal with the fact that it's UDP based. So looking at characteristics of video traffic, looking at the bottom first, the common, it still needs priority. It's still UDP based. It's still very sensitive to delay, and very sensitive to drops. However, it's not smooth and benign. Video is actually quite bursty and greedy. That is, the more bandwidth you give it, the more it will take. It'll take whatever you can throw at it, or it'll throw at you whatever you'll allow. And the more bandwidth that we have, the better our picture quality looks, right? Up to a certain point, that's definitely true. Whereas with voice, we have these fixed codecs that really run at their set speeds. And then it's very bursty. Why is video bursty, but voice is pretty smooth? Well, voice, first of all, unless I'm using VAD, voice activity detection, which is used for very low speed links. And the reason, what's the reason? Just seeing if you're paying attention to some of the previous information we've gone over. Right, that's the reason, is that if we have low speed links, we want to spare every last drop of bandwidth that we have so that we can use it for either other voice calls or the rest of our data. Maybe I've got 128K frame relay CIR. Now, that's maybe not very common at all anymore, but in some parts of the world, that's still, certainly in developing countries, there are still plenty of places that I consult with and talk to people that have very low speed links. And so bandwidth is still quite important. And so I've got a very low speed link, and I want to try to get 3 voice over IP calls onto that and still get some data. Well, there's not a lot of extra room there for the data. So we want to squeeze every last drop out. So voice activity detection stops transmitting voice and therefore stops transmitting packets when there is no voice. But aside from that tangent, unless we're using VAD, we're always sending the exact same codec, the exact same bandwidth worth of information in voice. Now with video, I won't get into the specifics, but we have, depending on the codec, especially if it's like the AVC, the Advanced Video Codec, which is basically H.264 and MPEG-4 combined, which is what everyone's commonly calls H.264, but that uses things like P frames, B frames, also keyframes, so predictive frames. Anyway, I won't get into all of it, but there are look ahead, look back algorithms But for the most part, we're never sending the entire video screen, all the pixels on the screen. It would consume way too much bandwidth. So instead, what there are called keyframes, which is that every so often, whatever the interval, however many frames we've decided is the appropriate interval to send a keyframe, that keyframe, we send the entire pixel screen. Maybe you've ever watched a video on TV or a video conference, and it will seem static, and all of a sudden part of the video will move, but the rest of it won't really catch up for a while, and then there will be a whole screen refresh. Well, that's because they've spanned the keyframes too far out from one another. You know, maybe they've made them every 300 frames as a keyframe or something. Maybe that's too much. Maybe it's not. Just depends on your environment. But the more often that we have these keyframes, we're going to have these bursts of a lot of video. And it's one of the reasons we'll talk about the 20% overhead rule, but we'll get to that. So anyway, video is very bursty and greedy, but the rest are about the same. Characteristics of most data traffic. It can be smooth or it can be bursty. It's typically the latter, just depends on the type of data. Data can be benign or it can be greedy. Again, typically the latter, depends on the type of traffic. Now, this is with a grain of salt, okay? So it depends on the type of traffic. I'm going to always say that. Any good engineering answer is it depends. But for the most part, data traffic is drop insensitive. And it's also delay insensitive. So if you think about a HTTP web request, right? The person on the other end, I might be sensitive to how it, how much delay there is before it returns, or if there's a drop and there has to be a TCP retransmit because HTTP is based on TCP. And so that just adds to my human understanding of delay. Okay. But the traffic itself is actually insensitive to that, because it doesn't matter how long it takes for it to get there. It'll get there. As long as there's enough bandwidth and I don't lose too many, if I don't have 20% packet loss, then the TCP packet will get to the other side and it will get in the right order. And if I drop a packet, it will retransmit. And as long as I don't have, like I said, too much packet loss, I will see the screen update. I will see the web page finally display. Okay, so the human might care about it, but that's not what we're talking about. We're talking about the traffic and the protocols themselves. And of course, applications that run with UDP-based information, these are more drop and delay sensitive. But then again, they typically are the ones that are smooth and benign as well. So this is where we can allow, or depending on the type of traffic, be a little more aggressive with policing and not allowing our data traffic to have quite as much reign and rule as it would like, being bursty and greedy, and give that priority and guaranteed bandwidth to our voice and video and signaling traffic. Looking again at the ITU-T G.114 spec for acceptable one-way delay, we have to, for voice, have, or at least the spec states that we should have less than or equal to 150 milliseconds of one-way delay, so a round trip of 300. This takes into account all the types of delay: DSP, packetization, serialization, propagation, and dejitter. Not just the actual network delay. This is the reason we've said it before, say it again, a simple ping test, which is a round trip, is not an adequate indicator. What you can use is on Cisco routers, there is the IP-SLA, what used to be called the RTR responder. This will actually, or of course you can use a third-party product that does the same thing, but this will actually packetize or simulate the DSP packetization, the encoding and sampling and quantization, and send a voice packet. So that'll take the serialization, the propagation delay into account, and then have it returned, and it will tell you the two-way, or easily divisible by two, so one-way delay for your traffic. And you can actually set this up, the IP-SLA, or service level agreement. IP-SLA is the command, IP space SLA. Read more about that. You can use this to set up regular monitoring for your network, or just baseline testing. So 150 to 400 milliseconds is acceptable only if everyone's aware of it, but it gets into the walkie-talkie conversation type of a characteristic. And above 400 milliseconds, unless you're on satellite, this is unacceptable for most people. Okay, so again, we're trying to be under 150 milliseconds one way. Dealing with jitter, packet loss, and bandwidth. So in terms of what these need, jitter needs to be less than 30 milliseconds one way. Now, delay is less than 150 milliseconds. Jitter, remember, is the variance between delay. So with all the different hops we have, we need to have each and every one of them under 30 milliseconds difference or jitter between one another. Packet loss needs to be less than 1%. Voice bandwidth, again, depending on the codec, can be roughly 17 to 106 kilobits per second per call. This is excluding dealing with IPsec tunnels and things like that, GRE tunnels. So if we're doing Cisco's V3PN, which is an older terminology, but still is very applicable today. V3PN was voice, video, and data over VPN, over virtual private network, and it dealt with a GRE tunnel inside of an IPsec tunnel. And the GRE tunnel adds overhead, and the IPsec adds overhead because they each add additional headers. And if we were dealing with MPLS or, something like that, that's going to add an additional header. So again, it really is going to depend on exactly what codec and exactly what layer 2 mechanism, and if there's any encapsulated security or generic router encapsulation, the GRE or anything like that. But this is just a rough estimate. And then depending on the signaling protocol used, the signaling, so not that before was the actual media, the 17 to 106, but the signaling protocol could be between 150 and 1000 bits per second. So just remember the base is 150 bits per second. Now that's not 150 kilobits per second, that's 150 bits per second. So we're talking like, 2 of those is 3 and 3 of those is 9. So we're talking 6 calls worth of signaling in less than 1 kilobit per second. Okay, so the signaling is very, very small. And again, the signaling does depend. Is it skinny or is it SIP? SIP takes a little more. Is it, just remember that skinny's skinnier. And if it's secure skinny, that's going to take more than skinny. If it's secure SIP, that's going to take more than just regular SIP, okay? But the base to remember is 150. The reason I'm saying that is these are perfect test-like questions. I'm not saying you're going to see that on your exam. I'm simply saying these make for perfect test-like questions, okay? Anyway, video bandwidth. So again, video bandwidth is going to use as much bandwidth as we allow it to. So whatever video rate we have configured with regions or has been negotiated, we're always going to add 20% of overhead for keyframing and other information, other bursts of video. So we use regions and locations to define these, and we're obviously going to go a lot more in depth on those. In fact, that's coming up after the QoS lecture, I believe, is where we've placed it. And so, for instance, a 384 kilobit per second call, which is a relatively low bandwidth call, not necessarily the best quality by any means. It's not a telepresence 5 megabit per second call per panel, but it's adequate for, a standard IP phone. But that's going to require 460 or 461 kilobits per second. So the math is 384 times 1.2. 1 is the whole. 1.2, 20% is 460.8 or 461. So how we implement quality of service. We can do this by command line, and Cisco even says you can do it by command line or by command line using MQC. And what they mean there is that, first of all, we'll talk about MQC. MQC is actually an acronym of acronyms. It stands for Modular QoS CLI, or Modular Quality of Service Command Line Interface. So they also mention, and this modular QoS command line it basically builds nested structures. And we're going to take a look at length in to these nested structures. So we build class maps, those go into policy maps, and then we put the policy maps either onto the interface, or we can even nest those further within other policy maps. And we'll take a look at both of those before we put those on the interface. But it uses this hierarchical structure. And so Cisco does mention that we could just do this using command line, period. And what this means is that there is a lot of older QoS commands we won't go over. Something that used to be called custom queuing and basic fair queuing directly on the interface that offer very, very little in terms of flexibility, and things that we really haven't used, honestly, in over 12, 13 years now. Okay, so MQC, I think MQC came out in, was it either 2000, I believe it was with the 11.3 iOS train, but it's been out for about 12 years now. So that's what we're going to use for most things. We also could use something called Auto QoS, and we'll take a look at that on LAN switches and the WAN router. And Auto QoS is a way of auto provisioning everything, and it does a pretty decent job, especially on LAN switches, to even on WAN routers as well, to build a baseline infrastructure. Of course, you typically want to modify what it creates, but it can certainly build a good basic infrastructure of quality of service, expose a lot of the components that we'll use to tweak the variables or values. And then there's also the QoS Policy Manager. Okay, this is a network management solution tool that can be used to deploy QoS automated. There's 3 different models for QoS deployment. One is best effort, which really is no quality of service whatsoever. The other is IntServe, stands for Integrated Services, and it uses RSVP. Now, one of the downsides is that every router in the path must support this. And I want to just draw a quick distinction, and then we'll come back to it in a couple videos and talk a lot more about it. But when I say that every router must support RSVP, this is RSVP with IntServe, with Integrated Services. If we're dealing with RSVP as a CAC only or call admission control only mechanism, as we will discuss a lot more, RSVP does not have to be on every router. Okay, but as we're looking at it here for quality of service, not for call admission control, but for quality of service, where we're actually talking about guaranteeing bandwidth, it has to be on every router. And so applications basically signal the network control plane. They signal the RSVP protocol to inform or instruct the router that they need a level of quality of service, or that they are the application that they say they are, and then whatever we've configured on the router using integrated services sees that RSVP, sees the trigger, and then dynamically provisions that bandwidth for them and takes it out of its available bandwidth for the rest of the traffic for quality of service. Okay, that's integrated services. It's integrated with RSVP. It's integrated with the applications. The applications actually signal the routers to tell them that they need the bandwidth. Then there's actually differentiated services as the third model. DiffServe, the network does the work of actually classifying the traffic. So the applications don't signal to the routers that they're using any particular type, okay? And so the network does the work of classifying with either access control lists or intelligent mechanisms that we have in the router that we'll take a look at, called NBAR, which is Network-Based Application Recognition, is what that stands for, NBAR. But it does the work of classifying the different types of traffic and assigning various DSCP markings to place them ultimately into the appropriate QoS classes that we've defined, and then they get the treatment that we've defined for those classes. And DiffServe is what we use today and what most of the world uses for quality of service. So DiffServe, what we use today. Because not every device in the IP path must support DiffServe to make it work, it can still be very effective. and it therefore inherently becomes the most scalable and therefore the most deployed QoS model today. So taking a look at some of the terminology, we see DSCP, or Differentiated Services Code Point. Okay, that's what that stands for. And this is a value in the IP header that we'll be taking a lot more of a look at here in a moment. And it's used to classify or define the various type of traffic that's within the rest of the payload of that packet. But this is a value in the IP layer 3 header. Then there's a BA, a behavior aggregate. This is a grouping of packets together with the same DSCP values. So it's basically saying the behavior aggregate, or the BA, is all the traffic within a given class. And then there is the PHB, or the per hop behavior. This is the forwarding behavior applied to an aggregate class or to a BA at any given node in the network. So let's take a look at what is QoS comprised of. QoS is really a suite of different mechanisms. So we're going to take a look at a lot of different mechanisms that fundamentally and theoretically pervade, whether it's the WAN router or the LAN-based switched environment. So the first thing that we always have to do is we have to classify our traffic. Now, we can classify our traffic, or well, I should say something on the network has to do that. Whether it's the actual endpoint itself, let's say a phone or a video conference unit that classifies its own traffic and really marks its own traffic, and we choose to trust that. Or if it doesn't classify, doesn't mark its own traffic at all, or doesn't do it properly, or we just don't want to trust it, we can classify that traffic at the ingress, so at the closest place possible to the end device. And if we can't do it at that closest place to the device, let's say it's an IP phone plugged into a Catalyst 3750 switch, if we can't classify it at the 3750, then we'll do it at the next closest device, wherever we can classify it. And so we're going to classify it using some method. Like I mentioned briefly earlier, there's NBAR, Network-Based Application Recognition, a special engine in routers that can take a look at packets and really specific characteristics of those packets and classify the types of traffic, whether it's a simple based on port number and other things, whether it's a basic ACL or access control list that we're not using to control traffic per se, but we're using to define interesting traffic, that is, use the mechanisms within an access control list in order to define or match what traffic we think is interesting for a given class. And then once we've classified that, we need to make sure that it's marked properly. So we need to put some sort of a layer 2 or layer 3, or probably both, depending on where the Ethernet frame at layer 2 or IP layer 3 value happens to be. You know, if we happen to be transmitting on a switch, we'll have a layer 2 value. If we're transmitting on a router, we'll have a layer 3 value. And of course, the packet will still have that layer 3 value even on a switch. It's just inside of the layer 3 IP header, but there's also a layer 2 layer 2 Ethernet or other layer 2 mechanism header there as well. And we'll take a look at those in a little bit more detail. But we need to classify and mark the traffic that's going to be treated differently. Next, we have, as you see, with the fairly nice graphic, I think, the queuing and dropping. So this is where we manage our traffic and sort it. And then we've got post-queuing operations where we're going to process that traffic and finally send it onto the wire. So some of the things that we can use for that middle section, queuing and dropping, we can use something called policing. This basically determines whether packets are conforming to our defined rates and we take action accordingly based on if they are conforming, then we probably transmit them. We can do other things as well. If they are violating our actions or exceeding them, we can certainly drop them, or we can do other things like mark their previously marked DSCP value. We can mark that down to a less desirable value. We'll take a look at all of these in a lot more detail. Next, we have scheduling. So this is also known as congestion management and congestion avoidance, and the two are very different. Congestion management includes queuing, and congestion avoidance includes selective dropping. So we use these scheduling tools to determine how a frame or a packet exits a device, a switch or a router. And queuing algorithms are activated, and this is a very important thing to note. Queuing algorithms are only activated when a device is actually experiencing congestion, and then they're deactivated when the congestion clears. Now, other than something we're going to talk about priority, strict priority queuing, other than that, if I say that an application has guaranteed bandwidth or a class of type of traffic, as we just mentioned, a BA, a behavior aggregate, the entire class could be comprised of a single application, or it could be multiple different types of applications. But regardless, if I give it a guaranteed bandwidth, there is no guarantee unless all of a sudden all of the bandwidth becomes saturated or congested. Until there is actually congestion, we don't need to guarantee any particular bandwidth, right? Because there's plenty enough bandwidth for everyone. But if we guarantee, let's say, 30 kilobits per second of bandwidth, and there's 100 kilobits available, but then all of a sudden an application that's kind of bursty and greedy begins using a bunch of it, and it uses up to 65%, well, there's still 35% available, or sorry, 35K available. Well, there's still more than enough, so we don't even activate it yet. All of a sudden it creeps up on 70K, and there's still 30K. We still don't need to activate it. Then it tries to creep into 71K. And now it's eating into 1K of what we should have as our guaranteed bandwidth. And that's the time when our guaranteed bandwidth queues will take over and say, no way, you can't go over this amount because there's some reserved for this particular application or class. Okay, but it's only one congestion is present. And then we have link-specific mechanisms. So these are specific to the type of egress layer 2 link that we're leaving. If we're leaving frame relay, we might have frame relay traffic shaping. If we're leaving MPLS, we might have things specific to MPLS. But depending on the link that we're leaving, the speed, and the type of layer 2 mechanism that is transmitting, we're going to have different things. So some of these are traffic shaping, fragmentation, we'll look at, compression, and then the TX ring or the transmit ring. So taking a look at some of these on the WAN, and then we'll take a look at some of them on the LAN, just in terms of what we have available to us. And then we will go ahead and take a much deeper look into each of these. So we can certainly do classification and marking on really every device. So on the WAN, CS3 is the best practice today for marking signaling traffic. Now we're going to get into all of these DSCP per hop behaviors. This is what's known as a DSCP PHB or per hop behavior. But I just wanted to go ahead and point out that it's important to note that while CUCM, the Cisco Unified Communication Manager, and the phones mark the DSCP properly, that voice over IP dial peers and MGCP on the gateways, so SIP, H323, and MGCP on the gateways in iOS, they still all mark their signaling traffic to a different per hop behavior, an older one called AF31. So there are places that we will need to make changes. We can do policing. Options for policing are older, CAR, committed access rate, and the newer way that we typically do things today is with class-based policing. So this is just like it sounds. It's a policeman saying, hey, you can only go 35 miles per hour or 20 kilometers per hour or whatever the speed limit is. If you try to go faster than that, I'm going to give you a ticket. And the ticket might just be that I drop you. So maybe it will, just kill the person, kill the packet is what it would do. Or give them a ticket, maybe mark them their DSCP, previously marked DSCP value down to a lower, less desirable one. But that's policing. Queuing, the various kinds of queuing that we had available to us throughout the years. Let's just mention these real quick. FIFO is basically the default queuing, first in, first out. Okay, there's also LIFO, L-I-F-O, which is last in, first out. Okay, but FIFO, so first in, first out. There's also something called priority queuing. We're going to use priority queuing. Strict priority queuing is another way of saying priority queuing. And strict priority basically means if you are in a queue that is given priority or strict priority, same thing. There's no difference between the two. Just you might hear it said two different ways. So I want to make sure there's to clear up any confusion that might occur. But priority queuing means that you not only have guaranteed bandwidth in time of congestion, but you also have strict priority, which means that if your packet is in this queue or in this class, you get out to the wire before all other packets in all other classes. Okay? And you can set up multiple priority queues, maybe one for voice, one for video. They're both strict priority. It's just that, whichever one is first will be serviced first, and it will get all of everything out till it's emptied. It'll go on to the next priority queue. Everything will be emptied from that priority queue before the router or switch goes on and transmits the rest of the traffic in all the other classes, if there was any congestion. Okay, so then we have CQ, something called custom queuing. As I mentioned, this was an older way of doing things. This was the command line only, and there's no modularity or no hierarchical structure to it. And this is very old. We're not even going to cover it at all, other than to say it was a form of queuing out there. Then there was weighted fair queuing, which was certainly an improvement from custom queuing, but still had its drawbacks. And then we got to class-based weighted fair queuing. So we not only had the benefits of weighted fair queuing, where we could give a level of fairness to everyone in the queue, but we could also weight different applications differently. But now with class-based weighted fair queuing, or CB-WFQ, we could begin to divide our applications or aggregate applications, our BAs, up into classes, and then give the fair queuing out to the actual transmit interface weights based on those classes. So it gave us a very modular, structured approach. And then we have something called LLQ, which is low latency queuing. Now, this isn't really a new queuing architecture itself. It's basically class-based weighted fair queuing with a priority queue. Okay, so class-based weighted fair queuing with priority queuing is what's known as low latency queuing, or LLQ, and that's what we use today. So we still use this CB-WFQ, and we still use the priority queue. Then for congestion avoidance, so that is congestion management, the queuing, congestion management. The congestion avoidance can deal with policing, but it also can deal with red or weighted red. So red is random early detection. I call it random early discard because that's what it does. It randomly selects packets early on before they should be transmitted and discards them, throws them away. Now, nobody uses red anymore. They use weighted red, where we can actually, I shouldn't say that. Some people, there might be applications for red, actually, come to think of it. But most people use weighted red for some things. And so the idea is that based on, and there's also DSCP-based weighted red, but weighted red, we're going to weigh the different types of applications and discard packets based on weight or DSCP-based weighted read gives us the ability to look at DSCP values, and we choose which DSCP values will be dropped and which ones won't, and which ones will be dropped more often than other packets based on their DSCP value. Then we have shaping. So now we're getting into the link-specific mechanisms. Shaping. We have frame relay traffic shaping and generic traffic shaping, which is also known as class-based shaping. We're going to talk more about why we're doing all these things. We're just listing what there is first. Frame relay traffic shaping is traffic shaping for frame relay specific interfaces, and generic traffic shaping is basically for everything else. And then we have other link-specific mechanisms like compression, I mentioned traffic shaping, and then link fragmentation and interleaving. So we'll talk more about fragmentation. The two types are FRF.12, which is the Frame Relay Foundation's call for call number 12 for fragmentation on frame relay specific links, and then multi-link PPP. So we can do fragmentation over multi-link PPP. Pretty much PPP is a layer 3 protocol that can be basically put on top of any other layer 2 protocol. It's actually a layer 2/layer 3 protocol. So it's got a component of both, and because of that, we can put IP into PPP, and then we can put PPP on top of just about any other layer 2 protocol, and we can do, as long as it's a multi-link PPP, even if we don't have multiple links, we can still configure it that way. Then we can do fragmentation. We'll talk about why we want to do these in a moment. With the LAN, again, we have classification and marking. With classification, we can either do explicit classification, so let's say based on access lists, or we can do what's called a trust. If we're trusting, let's say we're a switch and there's a phone attached to us, we might just want to trust it. Maybe it's a server and we know it's a CUCM server, it never changes switch port. So we might do an outright trust, that is trust DSCP, or trust, well, it would be layer 3 DSCP. But maybe it's a phone, but we don't know if somebody might unplug their phone and plug in their computer. And maybe they've cleverly written a program that marks all of their traffic with a certain DSCP value. We can conditionally trust things. To conditionally trust is to say, trust device if it's a Cisco IP phone, and then if it is, then trust either the layer 2 or the layer 3 value. But we're not going to trust if it's not a Cisco IP phone. How does it know? How does the switch know? Through CDP or LLDP med. So we can trust it only if it's who it says it is. If it is who we want it to be, an IP phone. Okay, marking. Do we want to do marking at layer 3 or layer 2 class of service? So there's layer 3 DSCP. We're going to take a look more at both of these. In fact, that's what's coming up next. We're also going to take a look at layer 2 class of service. Now, this isn't class of service like phone dialing permissions. We'll talk more about that. This is QoS network infrastructure, layer 2 class of service, or COS. And the only way that we can actually have a layer 2 COS marking is if we have the proper header for it. And it does not have any place in an Ethernet header. It only fits within an 802.1q header, which uses what are known as 802.1p bits. So 802.1p over the 802.1q header. Then we can do mapping. So if we had trusted, if it was an IP phone, we trusted layer 2 COS markings, well, the layer 3 DSCP markings need to be done. Now, maybe the phone had marked those as well, but maybe it hadn't. So we can map layer 2 class of service markings to layer 3 DSCP mappings or markings. We can also map layer 3 back to layer 2, and we can even map layer 3 to layer 3. This is, we can change the layer 3 marking basically. On a router, we typically do queuing at the egress, that is the output. On a switch, we have a lot more power to the switch. We might have a lot more command options in a router, so a lot more flexibility, but they're typically not as powerful in terms of their line speed rates, whereas a switch has ASICs, or application-specific ICs, or integrated circuits, and we've got a lot more capabilities in terms of line speed rate in a LAN switch, and we also have a lot more hardware queuing options. So we've got ingress interface queuing. Every interface is going to have an ingress queuing option and egress queuing. Now, the types of queuing, how many queues, how many hardware queues you have, that's going to depend on the type of switch, and we'll talk more about that in the demo. Then we also have something called scavenger traffic policing. So this is based on the classification of the traffic and based on what we've marked it to, we are going to have a class of traffic that we'll take a look at which class it is in a moment, that we basically call scavenger class. It is traffic that is less than desirable on our network. This isn't email or FTP or file transfers. This is things like, and it just depends on your environment, depends on what you deem as less than important. Maybe YouTube is a very crucial part of your business, so you don't want to make it less than important. Maybe it's not at all a crucial part of your business, so YouTube might be less than desirable traffic. Maybe peer-to-peer file sharing, or whatever it is that we might want to classify, we would put into here. Certainly any type of new worm or virus or something that is has some sort of a signature, something that we can classify fairly well, we might want to put into a scavenger traffic. Not that we don't want to get rid of it altogether, but we can hopefully have the network at least slow it down, if not get rid of it altogether. And with that scavenger traffic policing, we're not only limiting its rate, but we might actually just drop it altogether. We might do what's called a policed DSCP. So this is where changing the previously set DSCP marking down to a less desirable marking so that future devices can rate limit that offending traffic. We have different options. We have what's called microflow or aggregate for policing. So microflow is per flow of traffic, or per, if I have an FTP stream, but there's 20 people that do each stream of FTP traffic, or each stream of HTTP, or whatever it is a separate flow. So that's microflow is per flow. Aggregate is all of them. We can do it on an interface or on an entire VLAN. We have memory and buffers that we can tweak, and we're going to look in depth at on the LAN demonstration here coming up. And then we also have something called weighted tail drop thresholds, also something we'll take a look at in depth.